Bronsted-Lowry, Mike Lowry. Bad boys, what you gonna do? Mike Lowry. You guys, bad boys. He's one of the bad boys. That's Will Smith, right? Bad boys, what you gonna do? What you gonna do when they come for you? But that, nobody knows the words of that song. Arrhenius theory. We know we're going to look at all these different theories here, of course, but this is Chem 20 basically. Acids ionize in water to release H+ ions. Bases dissociate in water to release hydroxide ions. That was Arrhenius' theory. That was the first one he came up with. And remember, we actually do a lab in this in Chem 20. We go to lab and we say, hey, does this actually work out? And you found, like, for example, NH3 is a base, but there's no hydroxide in NH3. So then there was a problem with that. So then he came up with the modified Arrhenius theory, and he said, modified Arrhenius theory says acids react with water to produce H3O+ ions, and bases react with water to produce hydroxide ions. So we actually have water as a reactant there, okay? We're going to come up with another one here. Last one, and this is the most important one here, is the Bronsted-Lowry theory. Acids are proton donors in a chemical reaction, and bases are proton acceptors in a chemical reaction. So acids donate protons, okay, are proton H+ donors. Bases are proton acceptors, H+ acceptors. All right, and we've actually seen that with the reactions we've done so far. If you think back to, for example, HCl. HCl, H donates an H+, right, to water, basically, to make H3O+. That's a proton donor. In that case, water actually is a proton acceptor in that case, and we'll talk about that in a second here, okay? A chemical's classification as a Bronsted-Lowry acid or a Bl base is specific to a particular reaction. So each reaction is different, all right, is what they're saying. So it's specific for that particular reaction, all right. When we say Bl acid, Bl base, we're of course talking about Bronsted-Lowry, Bronsted-Lowry acid, Bronsted-Lowry base. We're not going to write that out, you know, Bronsted-Lowry every time. We're just going to call it Bl base and a Bl acid, okay. All right. So it is specific to each particular reaction, right? So here's these three reactions that you guys had written down here, and we're going to take a look at what are these Bronsted-Lowry acids, Bronsted-Lowry bases. So hopefully this will show up here, I guess. When we look at HCl, you'll notice that first of all, HCl is a strong acid, yes? So we have single arrow, quantitative, yes? Bronsted-Lowry acid, Bronsted-Lowry base. So this is your Bl acid here, of course, proton donor, okay? And this would be your Bl base in this case here, okay? In that case there, all right? And what we usually do here is we show the H+ moving over here like this. You can either do it up here or whatever, but we're going to show you the H+ being added onto there, okay? So Bronsted-Lowry acid, in this case, water is your Bronsted-Lowry base. It is the proton acceptor, all right? So donates protons, donates H+, accepts H+, the Bl base, all right? Let's take a look at the next one here. What's happening in this case here? Okay, NH3 and water. Out of these two, which one, if you look at the other side there, guys, which one is the acid acting as the Bronsted-Lowry acid in this case here? Is it water or NH3? Which one is donating the proton? Look at the other side to see what you end up with. Which one accepts the proton? Right? H2O should be your Bronsted-Lowry acid, yes? Correct? The H coming from the water is getting added onto the NH3. H+ comes from water, adds itself onto NH3 to get NH4+. So this is the Bronsted-Lowry acid. Look, this is the Bronsted-Lowry base in this case. And you would show me, for example, H+ goes that way, yes? Okay? Think about which way the H+ is going, right? the H plus is coming from the water. Look what you have on the right-hand side. How do you get from NH3 to NH4 plus? You have to add an H plus on. H plus, accepting that, right, is a base. Donating that is the acid. But remember, this equation is in equilibrium, yes? So what about the other side? Now, we talked about going that way, but what if we talk about coming back this way now, going back towards the reactant side? Out of these two here, which one is the acid, which one is the base? Which one is donating the proton, the H plus? Which one is accepting it? So you got to compare them, right? This side to this side here. This is now donating the proton. It is giving off the H plus to get back to NH3. And what is accepting that? Well, your hydroxide accepts H plus to give you H2O, water, HOH, right? So in this case here, we have two sides to this. And once again, you're going to put in here H plus, like so. Okay? So you're going to show me that that H plus goes to the OH minus to give you water and an H3. Okay, going back the other way. All right? Take a look at this one here. I'll give you guys a second here. You guys think about that one right there. Which one is the acid? Which one is the base there on both sides? On the left side, which one is the Bronsted-Lowry acid? HCN or NH3? Somebody, anyone? HCN, okay? So this is your Bronsted-Lowry acid, which I guess means that this is your Bronsted-Lowry base here. Okay. H plus is moving that way if you wish. Okay. And then if you look at the other side, right? Once again, acid or base here. Let's see, NH4 plus turns into what? NH3. So it has to get rid of an H plus. Basically, it's going to be donating that. So this turns into a Bronsted-Lowry acid here. This is your Bronsted-Lowry base here. Like so. Okay? Good? All right. So those are some definitions, basically Bronsted-Lowry acid base. And we'll be talking about those throughout the rest of this time here. But, you know, there's always some kind of question about which one of these is the Bronsted-Lowry acid, which one's the Bronsted-Lowry base. Diploma questions, unit test questions for sure. Okay? So those are pretty quick to do. So that's why they make good diploma questions, because really give you this equation here and they say which one is the Bronsted-Lowry acid, which one's the Bronsted-Lowry base. They might only give you, you might say, how am I going to pick which side or whatever? Well, they're only going to give you, you know, these two options here, and then they'll come up with some different ones or something like that, you know. So there's going to be a clear answer, of course. It'll make sense, but just so you know. Okay. I think you guys need to copy this, yeah? Chemicals that have the ability to behave as either a Bronsted-Lowry acid or a Bronsted-Lowry base are what we call amphiprotic. Always questions about this on tests, diplomas, etc. Amphiprotic. The general form of the amphiprotic looks like this, HA minus. It doesn't have to look like that. Obviously, for example, H2O doesn't look like that. Get your data booklets out. And this is important. If you want a tough question for figuring out KAs and KBs, these are the ones. These ones have, you do some work before we actually get to that. We're going to show you an example here coming up. Common amphiprotic substances include H2O, HCO3 minus, HSO3 minus, H2PO4 minus, etc., etc. What they're saying basically is if you look at these, let's find this one here, guys. HCO3 minus, for example. I guess we could have started with water, it's even easier, but HCO3 minus. Is it on the left side or the right side? If the answer is, if your data booklet, it's on both sides somewhere. Okay? If it's on both sides, HCO3 minus is on the left side. If you look close enough, HCO3 hydrogen carbonate ion is on the right-hand side as well. Okay? So it's on both sides. Therefore, we call that amphiprotic. Could act as an acid, could act as a base. You'll notice, you'll kind of get to know there's about 6, roughly, or 6 or 7 in your data book that it is. All right, and over time, you kind of get familiar with some of these that do that. But you have to be very careful. If you have this, and that's going to be a little bit of predicting reactions, which is tomorrow's lesson, which is probably the tougher one. You get that. You do have to be very careful that you know what is this substance acting as. Is it behaving like an acid or is it base? And there's a little test for that, of course. You'll notice that I'll kind of give you a little hint here. That kind of is a derivative if you want. If you lost an H plus, for example, you would get HCO3 minus. If I lose another H plus, I get CO3 2 minus. So it's kind of those ones that have H2CO3, H2SO3 kind of thing. So something like that. HSO3 minus would be the next one. After that would be SO3 2 minus. Okay? So basically it's those polyprotic acids that you're kind of looking at there for these. This was H2PO4 minus. It came probably from H3PO4. Okay? If you lose an H plus, you get H2PO4 minus. If you lose another H plus, you get HPO4 2 minus. Okay? And that's kind of how those amphiprotic ones work. So like I said, if you kind of see this kind of thing here, you think, hey, that had an H plus added onto this H2CO3, and it could also lose an H plus from this one here. It's kind of in the middle. Do you know what I'm saying? H2CO3 was probably the acid, and then I got HCO3 minus, which could be an acid or a base, and then after that I got CO3 2 minus kind of thing. So there's kind of 3 steps to it. Do you know what I'm saying? Same with this one here. This was probably H2SO3, and then it's HSO3 minus, and then it could be SO3 2 minus if you keep losing H pluses kind of thing. Okay? So just kind of keep that in mind. Like I said, there's about 6. I don't remember the exact number. 6 or 7 that are on your data booklet there, and you'll see those over time. The pH of an amphiprotic substance can be determined by first comparing Ka and Kb values. So I'll let you guys copy that down. Then we're going to do that. To compare them, if the Ka is larger than the Kb, then the solution will be deemed to be acidic. And if Kb is larger than the Ka, then the solution is basic. All right. And we'll take a look at that problem here. That kind of, nothing too tricky there, I think, basically when we look at that. However, if we're going to calculate the pH of a 0.15 molar hydrogen carbonate ion here, we first, of course, notice, first things first, that this is amphiprotic, which means you're going to have some extra work to do. We're going to do the same stuff we did last day, calculating pH of this, of course. We know that this is a weak acid or perhaps a weak base. I'm not sure. But we're going to do the same stuff as last day. We're going to write out the equation, etc., etc. However, which equation are we writing out? Are we writing out the one for the acid, or are we writing out the one for the base? We really don't know right now because we don't know if this is behaving like an acid or a base. It really depends on how much this breaks up here. Okay, if Ka is larger than Kb, then we're going to assume it's an acid, and if Kb was bigger than Ka, then it's going to be a base. This is the part that's not really that, can be tricky a little bit. I shouldn't say not that intuitive, but it can be a little bit tricky here. So, first things first, the Ka value for HCO3 minus. So, you're going to look that up like you normally do, okay? The Ka value for HCO3 minus. So, find that in your data booklet. If HCO3 minus was an acid, you would see that it is in fact 4.7 times 10. Yes? True? Okay. Now, I suggest you get your booklets out here, guys, because I got to show you something. Now, what's the Kb value for HCO3 minus? Now, and the answer is, it is not, okay, Some of you guys might be tempted to, well, hopefully you guys know that Kb equals Kw over Ka, right? But the question is if this is the acid here, is it the opposite for this base here? And the answer is it's not, okay? What you now need to do is this. We found the Ka for the acid, HCO3 minus. What's the Kb for the base? Let's find Kb. Let's find this on the base side now. Find that on the base side somewhere. Okay? And where do you see that? HCO3 minus on the base side is way down here beside carbonic acid, yes? Okay? You'll notice that the Ka value, of course, is not the same as that one, right? Yes? So what we need to do now is take 1 times 10 to the negative 14 divided by that value there, which is 4.5 times 10 to the negative 7. Okay? That's how I would find the Kb for that value, or for that HCO3 minus. All right? You can't use the top number because that's when that one is behaving as an acid. I have to use the Ka of the base, basically, or the acid one that combines with that. Okay? So that works out to be 2.2 times 10 to the negative 8. So, is Ka larger or Kb larger? Kb is larger because it's times 10 to the negative 8, yes, compared to 10 to the... So this one is behaving as a base, all right? So if HCO3 minus is behaving as a base, when I react it with water, what does my equation look like? If it's behaving as a base, it has to produce what? OH minus, yes. Okay, how is that going to happen? Well, H plus is going to get added onto there, right? Yes? And you're going to get H2CO3, aqueous, and hydroxide, because it's behaving as a base. All right? So you got quite a little bit more work to do there in that case. You have to compare the Ka to the Kb values, and once again, you need to find the appropriate dissociation of constants that go appropriately with the acid and, in this case, the base, which are not. A lot of people are going to think this number here and that number should be the same, and they're not. Because when it's acting as an acid, the base of that is something completely different. It's obviously not acid. It's CO3 and that's the base, the acid, H2CO3. All right? So those two numbers aren't going to match up. They shouldn't, because they're in different spots according to your data booklet there. There you go. We said when we started this, now you can do the rest, guys. This is 0.15 molar, right? So we're going to start here. This is 0.15 molar. My Kb value is 2.2 times 10 to the negative 8, and I approximate that. Oh, sure I can, right? And then I would say, I would start with basically, well, X here and X here, yes? Right? I want to calculate the pH. So once again, unfortunately, you're going to have to find the pOH first. Kb is equal to x squared over 0.15. The Kb value, like I said, was 2.2 times 10 to the negative 8 here. Is x squared over 0.15. X squared is going to equal, let's see here. I'm not sure what x squared equals actually, and just to save a little time, I'll just leave that there. But x turns out to be 5.77 times 10 to the negative 5 molar. Okay, which of course is your hydroxide concentration. Okay. So now that I know the hydroxide concentration, I can go back up to here and say, you know, right here, this is 5.77 times 10 to the negative 5 moles per liter. I can find the pOH of that, which will work out to be about 4.238. And therefore I can find the pH from that, which will give me about 9.76 here. Final answer. Okay. All the bottom part is all the same as we did before with Ka and Kb values, of course. However, the trick with this was you had to, of course, first decide whether it was an acid or a base. We'll have a question for you to practice that again. And they're all the same, guys, for amphiprotic, but you have to kind of go through the example and make sure you kind of match it up and see how that all goes, right? Now, if it had behaved as an acid, well, it's a little bit quicker because you don't have to worry about POH stuff, right? So you do Ka, same thing, x squared 0.15. You'd use the Ka value instead, of course. You'd calculate x, but that would be for the hydronium ion. You take negative log, you're done. Okay. All right. We got a couple more, 2 or 3 pages more. They're quick. But any questions on this? Anyone? Questions, anyone? Okay. All right. So like I said, with amphiprotic, you will have to determine. This is another pretty common diploma unit test question. Once again, it's very quickly to do. So it's very, very easy if you pay attention to what I have to tell you in the next 2 slides here. It's very, very easy. Okay. And it's pretty straightforward. If we know what we're doing here. Conjugate acid-base pairs. I already told you about this, actually. I said for every acid, there's a base that goes with it, basically. That was funny. For every acid, there's a base that goes with it, basically. Conjugate, I'm on a roll today. Okay. Conjugate acid-base pairs, all right? Any proton transfer chemical system at equilibrium involves a Bronsted-Lowry acid and base in both forwards and reverse directions, of course. We saw that by H plus and OH, H proton donor, proton acceptor. Okay. All right. The ionization of acetic acid, for example. Ionization of acetic acid. What we're going to do is name the conjugate acid-base pairs for this. Once you get that copy. While we're waiting for you to do that there, when you're done copying it down, I want you guys to write out the Bronsted-Lowry, tell me which one the Bronsted-Lowry acid base is, show me the H plus proton donor, proton acceptor, show me which way the H plus is going for both sides here, of course, and then we'll talk about the conjugate acid-base pairs once you get that done. All right, so the ionization of acetic acid. Once again, take a look at this. This is going to be some of your homework here, but pretty common types of questions. Like I said, Bronsted-Lowry acid, which one's Bronsted-Lowry base? Well, how do you get from here basically over to this side here? It looks like H plus goes to here, H plus like so. So we'd call this the Bronsted-Lowry acid, and this of course would be the Bronsted-Lowry base. All right. And then if we look at the other side, which way is the H plus going? Looks like to me, how do I get from H3O plus back to water here? Looks like I'm going to be doing H plus there. So this would be the Bronsted-Lowry acid, the Bl acid, and this would be the Bl base. Proton acceptor, proton donor. Okay? Conjugate acid-base pairs basically say which one matches up with the other side here. Usually it's the difference of an H plus is what it is, all right? And they're going to tell you on the next side here. There's 2 acid-base pairs here. There is, for example, pair number 1 here. So pair number 1, they differ by an H plus. They have to be reactant product side, okay? Opposite sides of the arrow. Opposite sides, they differ by 1 H plus, guys. So the first pair would be CH3COOH, and the base that would go with that, all right, would be CH3COO minus. Differs by an H plus. Reactants, product side. Okay? Has to be. We get people picking stuff on the same side for some reason, on the other side for some reason. They have to be on opposite sides. The acid here, this acid makes this base here. Okay? Pair number 2, of course. Okay? Is, once again, and usually we write them as acid base. So acid base, H3O plus and H2O. Okay? Is the second pair. Differs by an H plus. Yes? Okay? Differs by a proton. So, all right. So acid-base pairs, reactant, have to have one side from the reactant, one from the product, and vice versa, of course. One from the reactant, product, of course, as well, depending on which way you're going with that reaction. So there's 2 pairs there. Conjugate acid-base pair is a pair of chemicals whose formula differ by only 1 proton. Okay. The stronger an acid is, the weaker its conjugate base is. So, when you look in your data booklet, they are organized by strongest to weakest, right? Even the weak, for example, the weak acids are strongest to weakest. We've talked about this before. So very strong acids here, completely ionized, and then strongest to weakest acids, which means opposite, strongest base to weakest base as you go up. Okay, it is like the table we did earlier with SOAs and SRAs, kind of. But real quick here, once again, so the stronger the acid, the weaker its conjugate base, right? So as always, guys, when you look at this table here, of course, and they'll probably ask you a question, something about strong acids, weak bases, kind of thing, organize them or something. Remember, the strong acids are at the top. As you go down, the acids become weaker, the bases get stronger. Right? So down here, the strongest base is hydroxide, and then as you go up here, they are strong, 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 and then they get weaker, weaker, weaker because the acid is the strongest, right? It's always in that balance, right? The stronger the acid is, the weaker the base is. If they got a strong base, the acid's comparatively quite weak, okay? So keep that in mind for that, all right?